Thank you so much for the invitation. Thanks for a great talk, Ray. That was a great start to the session. And my talk is teed up to very much follow and kind of add more detail on some of the ideas Ray brought up. Perfect. And so just to add to Ian's point from the work we do at Hopkins, so my lab focuses very heavily on machine learning and developing new machine learning strategies that will allow us to leverage data that are collected either within electronic health records or through wearables in order to do a collection. Essentially, the overarching goal is to be able to use such data to target delivery or to be able to and target delivery in a variety of ways, either being able to manage disease status or measure disease status in more precise ways so that we can identify when to intervene, whom to intervene, and how to intervene on. And we use the same platform technology in a variety of different disease areas. For today's talk, I'm going to focus very specifically on PD and then end with one or two other examples to broaden out how this isn't just specific to PD, but I think broadly applicable, which is really the goal of the new journal, Digital Biomarkers. So Ray mentioned a great deal about he mentioned a little bit about Empower and then the app preceding it, Hopkins PD, that we created back around 2013 when we started thinking about how can we use wearable mobile to measure disease status, changes in disease status in more detail. So I'm going to do a deep dive from about 2.5 years of work on trying to use this data to more comprehensively understand disease status. So I'll start with a brief hypothesis, new strategies for actually measuring disease status, and show some early results. So the main hypothesis here is kind of what Ray motivated, right? There are a number of symptoms that you can measure while this patient is at home. In Parkinson's in particular, this strategy is likely to be useful because many of these symptoms are the kinds of symptoms that phones can measure. So many of these are motor-related symptoms, so you can design tests specifically to measure those motor-related symptoms in using active tests, like tests you ask them to do of the kind that Ray described. You can also do a lot of interesting measurements in a passive way if you creatively think about how people use their phone and the GPS and things they're doing, and we embedded some of that in the Hopkins PD app, which was the precursor to Empower. And then in addition to that, from the data, you can get a lot of understanding of non-motor symptoms, for instance, things like depression, like the ideas you can get from, there's studies showing that tone of voice gives you a view into whether someone's depressed or not. Or the amount of movement, whether they're leaving the house or not, gives you a sense of sociability and sort of how they're feeling that day. So I think this is very exciting in terms of these sort of sensors that give you subtle cues. In other words, no single measurement may be precise in its own right, but by integrating a lot of these different types of measurements, you can get sort of a more comprehensive and holistic view. And so our goal today for this talk is going to be a sneak peek into using machine learning to integrate different types of data. And so in PD in particular, for instance, actually, can you raise your hand? How many of you in the room are PD researchers or particularly work in PD? Okay, so only a subset. Okay, so I'm going to, so it's not obvious to everybody. So PD patients experience daily fluctuations in disease severity, right? So within the course of a day alone, symptomology varies from several times, ebbs and flows over the course of a day. And how the variation takes place also depends on the stage, whether you're an early stage PD patient or a late stage PD patient. And also it varies across patients. And this principally drives your treatment strategy, how much dose to give them at what time. And the effect and the question of is the drug effective or not is and I'll show you some really interesting results where the notion of is the drug being effective or not really depends on, well, what time were you measuring the symptom? And if your success depends on that, being able to do that precisely is pretty important. At the moment, of course, the strategy is this patient comes into the clinic. That happens once every 3 months at best, which means you're getting very, very little sparse data. Moreover, also like Ray said, it's not very precise. So can we measure changes in disease severity using these digital markers as measured by sensors on a smartphone? And prior to our study, people had thought about, and I still think there are other promising strategies, had thought about trying to build very specialized devices like accelerometers that you put throughout the body. One of the big challenges with these very invasive devices is that patients don't really want to wear them, so your compliance is really low. The challenge of going down the path of smartphones is the data is very noisy. And so from a, can we work with the data and get value out of it, machine learning becomes very important because we have to think very hard about our strategy for teasing value out of this data. So here I'm going to talk about data that came out of the Hopkins PD app. And the first study started, like we said, this was back in 2014 when we launched. There was really no precedence at all for just using phones to collect this kind of data. It was pretty amazing to us that very rapidly, this was a study launched by Ray at the University of Rochester Medical Center. Very quickly, people started participating. They enrolled from over 70 different countries, which was very interesting. I think we had over, within the first 6 months alone, we had, this is, to date, we ran the study for a short period of time, like about a year, 587 users, 127,000 tests, 168,000 hours of passive monitoring data. And okay, so now so what's interesting is if we went back and looked at the data, this is the app that Ray described. There were basically 5 different active tests we were asking them to do. So walk, he described tapping, speech, turn around. And the interesting thing is if you look at any single modality alone, so in the examples that were being described above, if you looked at any single modality, like for instance in the walking test, here we're looking at speed. And so if you look at the before and so the after here is after getting a medication here, levodopa, you can actually see a difference in the pattern before and after in a variety of different, so this is the balance test where you're asking the patient before and after giving the dose, you're asking them to stand and you're measuring using the accelerometer, the balance. And there's a big difference you can see in what the balance looks like before and after for this patient. Now the interesting thing is if you look at any single test or any single type of measurement, there is a subset of patients, there may be a subset of patients on which there's very clear signal. And I'm cherry picking an example for you. But the challenge is for any given test, there's no single test that works really well for the entire population, right? So the question now really for us is, well, so if I had to cherry pick examples, I can show you a bunch of different these sorts of things I can imagine from the data, and every single one of them, I could cherry pick a few example patients and show you, and visually you can see a big difference. But the difference, there's no single test on which across the entire population the difference is so visually distinct, right? So now the question is, how do we get these subtle, first of all, is there even a notion of subtle signatures, right? What are they? Is there even sort of an opportunity for thinking about integrating these subtle signatures and how? And so here we're basically going to take the voice, balance, gait, and the walking test and the tap test and combine them in order to think about it. Okay, so quick sneak peek into how do we think about it. So typically, and so for those of you who focus on analytics, typically if you have a lot of data and you want to learn a score, what do? You treat that as a regression problem. So when I say the word treat that as a regression problem, can you quickly raise your hand just for me to get a sense for like, is that something totally clear to you? Some subset of you work in analytics, great. So all you're trying to do is to take data and turn that into some score, a numeric score, and if that numeric score is high, that's saying, it's turning a high-dimensional vector of vector of quantities or measurements into some score, and when that score is high, you may mean severity is high. When the score is low, severity is low. So that's what I mean by regression problem. Okay, in order to learn this from data, the challenge is typically the way we learn this from data is using the following strategy. You go and collect a bunch of measurements, right, like voice, gait, walking, etc., and then you need some gold standard measurement, right? So a gold standard measurement would be Ray explicitly doing an evaluation and asking, is this person, at level 5, level 4 severity, level 3, level 2, level 1? This assumes that there is a good gold standard strategy. The challenge with many of these diseases is there is no gold standard strategy. So in the absence of a gold standard strategy, what do you do, right? So this is what has hampered this field greatly. It's the lack of any other strategy in order to be able to regress against. Does that make sense? So we need an alternative. So here's an example type of alternative one can develop. So what we've developed is a new machine learning strategy. And what that allows you to do is to not assume that a gold standard exists, but instead it learns from really noisy weak cues. And here are the kinds of weak cues. So instead of saying you know what the severity level is, because you don't actually know, but if you could compare the severity at multiple different time points, so you could take, someone who's after levodopa versus before levodopa, and their fluctuators, then after levodopa, they're often feeling better. Before levodopa, the severity symptom is high. So while you don't know actually how to, give a particular score of severity or define the severity level, you have a very weak cue that looks like, well, they're probably feeling better after medication, especially if they're a fluctuator. Does that make sense? So in other words, you can exploit these what are called weak labels in order to be able to learn scores that allow you to uncover severity even though you didn't have a gold standard. And so we're going to use a strategy like that for Parkinson's. I'm going to skip all this. So just to kind of give you an idea, imagine we have from these 5 tests, we get lots of different data. We turn that into 230 different little markers that are extracted from the data. They look like basically these high dimensional signals, right? So it's a 230, and we need to somehow convert that into a score. We're going to use this weak supervision-based approach where we basically have weak cues based on before-after medication in order to train a signal. And now we're going to validate the gold standard signal we found against measures that are known in the field. So before I proceed, questions. Does this make sense? You can do a vigorous nod, and that will be good. Okay. So I'll skip the math, and now get to some interesting results, right? So really your main takeaway should be, in order for us to be able to even have these, historically the way we've approached these markers, digital biomarkers, is we look for very visible signal to noise ratio, right? High signal to noise ratio strategies. And with digital, because many of these are at home, they're messy, there's so much patient variability, chances of high signal to noise ratio is low. And in order to be successful, we will need 2 strategies. We will need to integrate lots of different types of markers, which each have subtle cue. 2, we'll need new strategies for actually coming up with these scores or measures, because we don't have validated gold standard measures to learn them from. Okay, so now let me show you some promising and interesting results. So here what we're doing is in Parkinson's, using the data we got from the mobile phone, I'm showing you some example patients. And on these patients, you can see each one of these. Here are 2 different example patients. The first one is a patient with no PD. The second patient is one with moderate to severe PD. So he has a Hoehn-Yahr stage 2 to 3. And here what you see is every dot is effectively a score that is automatically computed using the strategy, using a test they took on the phone. So they took a phone test, we collected the data, automatically in the back computation happened, it turned into a number. And then what this is showing is effectively you can see a huge amount of fluctuation on a day-to-day basis. This is the first time such a thing we've been able to measure such a thing, right? To date, there's really no, so in blue, what I'm showing you for this patient is every time they went to the clinic and someone like Ray, I think in this case Ray, did an actual UPDRS measurement, right? It took him 30 minutes to make that measurement. And for this example patient, because it's so expensive, they were, in this entire period, we only had 2 measurements. On the contrary, this person is taking this app
they're collecting these test data on a daily basis, and every day that they do a test, automatically this dot gets collected, and you can see whether it's before or after medication. You can see there's a huge amount of variability. Now the second example I'm giving you is one, instead of a person with no PD, is one with moderate to severe PD, and you can kind of see two things again here. One, the overall score is higher, right? So here, instead of the MPDS is the mobile Parkinson's disease severity score. That's what we're calling it. Here, instead of an MPDS being around 17, which is for the low no PD case, for someone with moderate to severe, it's around 60. So it's higher. So you not only get to measure an overall stable trajectory, around that you're measuring all this variation. And look at that, there's like a good 40-point variation here, right? Imagine you're running a trial, you happen to collect 4 data points or 5 data points, and now you're looking at that measurement. You're completely hosed. So here's a third example patient. On this patient, actually, this exact idea is illustrated. So here, this is a severe PD case, Honeyar stage 3, and here again, you see a huge amount of variability. Now it turns out we only had 3 UPDRS measurements, and you can see there's a huge amount of variability in UPDRS measurements. Now, obviously, your UPDRS measurements, the time of day makes a difference. So it's possible that when these 3 measurements were made, it happens to be in different states during the time of day, and it's hard to know, is this variability natural variability, is stable variability. But from this, you can get a very nice sense of both the long-term trajectory as well as intraday variability. Now, continuing with this, the same strategy here, what we're showing you is plots where, again, same thing. Automatically, the score is computed, and what this shows you is effectively 2 different patients for whom in red we're showing before medications, in green we're showing after medications. And what you can see here is basically automatically these are computed, right? So in blue, you can see kind of their stable trend. I'm showing you 2 different patients. In the patient below, they're getting worse over time. So you can actually see the MPDS, that's automatically computed, kind of captures this overall increasing trend. But simultaneously, you're also getting this daily fluctuations. And more importantly here, the thing to note is the daily fluctuations actually look like something that makes sense. That before severity, in many, many example cases, before you take your medication, your severity is higher. After you take your medication, your severity decreases, right? This sort of checks out with the way you'd expect it to behave. Now, when we go and tally these with UPDRS, so there's UPDRS part 3, which is just the motor component. There's UPDRS total score. This is like Ray judging me from a distance. There's timed up and go, and then there's the Hone and Yar. So these are 4 different scales that are all used to, you can think of them as no single one of them is a gold standard, but each one of them kind of captures some level of severity. And so what this is giving you is a way to correlate MPDS against these 4 completely different scales. And you can start to see that, while it doesn't have one correlation with any one, it sort of does pretty well capturing signal with all 4 of them. And here are the correlation measures. Finally, in this plot, what we've done is we've taken patients where, so this data is still private, please don't release it on the internet, but it's under peer review right now. So this is an example where someone with, we're using MPDS to measure patients in their on and off state, and we're measuring the actual, so in blue, we're showing the UPDRS scores, and in red, we're showing the MPDS. And what you can actually see is that if you had the ability to measure UPDRS all the time, in other words, if you went in and did all the due diligence, it's possible that UPDRS would allow you to measure variability. The challenge is it's just too expensive. It's not feasible. So in this example, what we did is we said, well, can we just go before, after, systematically measure UPDRS before, systematically measure UPDRS after, and similarly measure MPDS, and you can see they kind of track each other pretty nicely in terms of, reductions. So conclusions, what this is allowing you to do is effectively take, again, like I said, we collected 5 very different types of high dimensional signals. We're taking 238 different types of markers from it. We're coming up with a strategy to combine them and learn these from really messy data. And now the question is, and showing an example place where it might be possible in home to be able to measure severity level. And you could see how this could drive a whole bunch of new intervention strategies beyond just tracking for trial recruitment alone. So to end, I'll actually just give another example from my research. So while we spoke a lot about PD today, I think digital biomarkers, I feel, is a very broad area. So my lab is doing work in a variety of different areas. I'll give you this example in sepsis, but in lupus, scleroderma, cardiogenic shock, and this is work in sepsis. And here what we're trying to do is effectively, so one of the results we showed very early in our lab is that while people are again looking for these bioassays for diagnosing individuals at risk for sepsis or individuals with sepsis, turns out you can actually combine a large amount of data that is already routinely collected. If you could integrate them in a systematic way, you can identify individuals at risk for sepsis much more precisely than any single one of these diagnostics they currently use as part of standard of care. So this is really interesting because it again gives a new digital diagnostic strategy. And this is something that is now being deployed across 5 different hospitals at Hopkins as a trial. Similarly, you can use this to start measuring, like I said, responses to treatment. I showed you one example with a PD. We're trying the same kind of strategy in sepsis. You have a variety of different, because timeliness of treatment is so important, using electronic health record data to be able to measure response to therapy, that we see huge amount of variability at the patient level. So here I'm showing you examples where you're trying to aggressively manage blood pressure. There are a variety of different treatment options you can give. Different patients are responsive to different treatment options. Can you uncover for a given individual what their likely response is going to be so that you can develop a way to target the right therapy quicker? And with that, I'll conclude. Thank you.